can I go over it after the notes? Yeah. So, is that the one of the orbitals?
Yeah.
That was the one I wasn't sure if you guys. Oh, yeah, I was like, how many unpaired electrons are present? That one. I'll go over it in a second. Because it's written in a way that it's abnormal. It's not ground state. Okay. So, here we go. So Coulomb's law, we actually have talked about Coulomb's law a little bit before, about how charges attract if they are opposites, and how charges can repel if they are the same. So, for example, this is a...
Teacher, quick business interruption. If you will send Junior's last name A through L, Junior's last name A through L to the cafeteria this time. Thank you.
It won't be very long, guys, okay? But do communicate. I think y'all's group, Clayton, and then the other group is going together. So. Okay, so Coulomb's law is just... Excuse me? If you need more time, you need to email me because you guys will be separate. Y'all's I have pushed to Monday anyway because you're not going to be here. And then Alex, y'all's is Monday anyway. But just let me know timing-wise what you need. Okay, so let's get this started again. Whenever you're talking about attraction, you have to be talking about opposites attracting, right? So what we usually do is that to quantify the whole qualitative term opposites attract, we can actually talk about the forces of attraction, the quantity of the force, by multiplying the two charges that we're talking about. So for example, in an ionic compound, let's say lithium chloride. We have a positive 1 and we have a negative 1 for the lithium plus and the chlorine 1 minus. And the force of attraction is definitely related to the distance that separates the charges, but it's inverse related. So for example, if you have a great distance between the two opposite charges, that's going to decrease the force of attraction. And that's what you can see indicated by the inverse relationship between force and distance here. And a lot of times we don't actually quantify it. We talk about it. And like I just did, greater distance, decreased force, decreased distance, increased force of attraction. So, but this is a good way to show what Coulomb's law is and how it can be calculated. So what we'll do is we're going to look at the magnitude of the charges more specifically. So there's a couple things that are going to be involved in forces of attraction. We're actually going to talk about lattice energy, binding energy, and that's actually it today. That's really easy today. These are some things that are going to affect specifically lattice energy and lattices. You guys remember what a lattice is? Do I have it over here? Yeah, by myself, like this. This is a lattice, okay? And this is a sodium chlorine salt, and it's multiple attractions. These like gray things here, those are not bonds, right? They're not actually touching. They're just attracted. It's just like how else do you hold it together, right? So there's little gray things there. Huh? There's always a magnetic field between them. They're more attracted than bound, like physically bound, is what I'm saying. So it's more of an electromagnetic field. It's like more about its nuclear attractions because the electron cloud itself of chlorine is what's attracted to, I'm saying sodium chloride, right? Is attracted to the nucleus of sodium. So this electron cloud is attracted to the nucleus. So the nucleus and the electron cloud are not touching. That's why they don't touch. Yeah, good point. Okay, so the lattice energy is the energy that's actually holding, or the energy that it takes to break this crystalline structure apart. So it is usually an endothermic process. The energy to break it apart is requiring energy, so it's an endothermic process. But there are various variables that do affect the amount of energy you put into it. For example, the size of the charges. The magnitude is what that means, okay? The word for that is magnitude. And that's in the Coulombic attraction equation. That's what Q is representing. Q is charge. Second, so to actually compare that for you, what would be a good example of an ionic compound with a 3 plus and a 3 minus as their charges? Aluminum. Nitride. Aluminum nitride. Now the 3s are not there, but we know they're there, so that would actually have a much stronger attraction for itself, meaning a much larger lattice energy, versus something like we just did, sodium chloride, which has a lower magnitude charge product, is what we call it. The radius of these don't change significantly. They do change. My ionic radius group, we'll be talking about that. They do change slightly whenever they become their ion forms, but it's the less significant of the two options that's going to cause energy to go and increasing. So if you're ever talking about why the lattice energy is greater than something else, you're probably not going to reference size. You're probably going to reference magnitude of the charges. So what happens is whenever we do have ions that become smaller, which is greater or which is bigger, a cation or an anion of a particular type? Cation or anion is bigger, would you say, Josh? Or what did I just say? Did I say smaller or bigger? Let me start over. Which is smaller? Cation or anion? Can I get a vote? Okay, I cannot. Cation smaller. Oops. I want you to know that it's smaller. I won't say it like that. Right. So this one is smaller because it loses the ion, and so the electron, and as the electrons are less repulsive within the cloud gets smaller. So that is smaller. Okay, so let's look at this in a more quantitative way. We literally cannot quantify lattice energy just by measuring it. Cannot measure it. So what I want to do is I want to break apart a crystal, but I can't figure out the energy to do it. But I can do it in a step-by-step process like Hess's law. And Hess's law is something you're familiar with. I'll come back to that page if you need me to. The actual definition of lattice energy is on the board. I'm going to write that part down. It's very specific in the way that it happens. It's taking solid form to ion form, but it's not aqueous. It's not in solution. Water has no play, no role in this process. That would be like enthalpy of dissociation or something like that. That would be an aqueous solution. This one's taking, for example, lithium fluoride, solid, and breaking it into its two ions in gaseous form. Lithium plus gas and fluorine minus gas. That is how you write that equation. And that heat of lattice energy, or the energy associated with that, is called delta H LE for lattice energy. And that's what each of these numbers are representing. So what do you notice, like for example, for the chlorine example, lithium chloride 834, magnesium chloride 2326. Why is that lattice energy so much greater? Give me some more. I want you to say a good phrase for it. So higher charge, stronger attraction. That term for that is called a higher charge product. Okay, so greater charge product, because what's product mean in math terms? Math terms. Multiplication. So charge product literally means to multiply the charges, like we did with the Q1 times Q2. That's what that's referring to, charge product. Yeah.
Okay, so is this going to be like thermal where it's like...
Yes. The answer is yes.
Products minus reactants? Or no?
We actually won't be able to do products minus reactants because, like I said, you cannot measure really the energy of these separately than these. We're going to do it more Hess's law, doing summation of equations. That's what I'm going to show you next, okay?
So no aqueous solution would have the lattice energy period.
Because, I mean, the lattice energy is related to why an aqueous solution, when it's undergoing dissociation, why it's exothermic or why it's endothermic, but the lattice energy itself is not talking about the aqueous solution. It's just taking a solid and ripping it apart and then ionizing them, and then making them gaseous, which they're not gaseous. Like lithium at room temperature is what? What state of matter? Solid. Fluorine at room temperature.
Yes.
Gas, but it's not it's not just fluorine, it's SF2, it's diatomic. So like we have to morph these things into just their ions, and that's what I'm going to show you here, okay? So let's do a sodium chloride example. Okay, so what I want to do, and I've got it flipped here because I'm actually taking the two ions in their gaseous state and I'm making the solid. So if I told you lattice energy requires energy, was that endo or exo? Endo. So in this case, the way I've written it would be exo, simply because when these two things that are very like crazy gases and they come together, they're in their nice, stable, happy place, and they release all that pent-up energy, and they're releasing it as exothermic. So we're going to actually solve this with a bunch of different variables that you guys are researching right now, okay? So I'm going to walk you through step by step, but I'm going to do it I got to do it over here so I can show my people. All right, so this is the end equation we want. Okay, we want that. So write that towards, like, give yourself some space, maybe 5 or 6 lines, and write that at the bottom. And lies, this is the opposite, like just said, this is the opposite one. So flip the equation so we can actually find the lattice energy, so that we're not finding the opposite of lattice energy. We can always flip the sign in the end, but I just want to do it the correct way. We cannot measure it directly, so we must do it this way. Okay, so if this is what we want, the lattice energy of sodium chloride, which is the energy it takes to break it into its 2 ions, gaseous and gaseous. How do we get there? Well, the very first thing we need to probably consider is making sodium solid go to sodium gas, right? We're going to make this. Sodium solid going to sodium gas. What process is that?
Sublimation.
So close, yes. Sublimation would be our better guess because it's going straight from solid to gas. Delta H of sublimation, write down these values too, okay? For this one, Han, you're on a roll today. You are good. So that's our value for the H of sublimation of sodium. Okay, so I've got sodium in gaseous state. Is it an ion form yet? No, it's not an ion form. So I want to take this guy and I want to ionize it. How do I ionize it? So what ion am I making? Na gas plus, right? And then what's over here? 1 electron. What is that? What process is that? This group is ionization energy. So Clayton, so what is this? Thank you. This is the ionization energy, i.e. the energy it takes to take the neutral form to its cationic form, making 1 electron, or forming 1 electron, and that is 496 kilojoules per mole. Okay, so sodium is now to its ion form. Yay! We have this, and we want to keep this. See? Yeah. Okay. So now let's do the same for chlorine. How does chlorine naturally exist? Diatomic gas, right? Bless you and stuff. Okay. So chlorine gas, it's diatomic. What do I need to do to it first before I can ionize it? Yes, but I need to write the equation. I do need to do that. What do I need to do to chlorine? It's like this together, guys. Break it. Bond dissociation energy? Coming back? Okay. 2 chlorines, after you break it, it's 2 separate atoms of chlorine. They're still gas. Good. That's called BDE, bond dissociation energy. And the chlorine bond dissociation energy is 243 kilojoules. All right, Han, this is where you come in. So tell me what you said. Because I only need 1 chlorine in the end, so that's multiplied by 1/2, and the energy is multiplied by 1/2 because I know that I only need half of that energy to do it. Okay, so now I'm in chlorine gas. I'm still not to chlorine ion. What do I do?
More ionization.
Yeah, I'm making that one ionization energy made a cation.
Okay.
I have another.
So
How am I going to add it? So adding an electron is what Josh is saying. Okay, what does that make? Ion, which is great because that's what we want. Okay,
Yeah.
what process is this? Sure, what group are you guys? So doesn't that chlorine love that electron? Yeah, it does. So delta H, yay, the energy that's released when an atom gets an extra electron, it's like, woohoo, octet, yeah, chlorine minus chloride. So that is negative 349 kilojoules because that process is exothermic. It's releasing energy because it's happy to have that extra electron. So it now has octet and it's very stable. Okay, so now we have chloride on this side. Yay. So what am I missing from my process? Solid sodium chloride. So we remember how the formation stuff works, delta H of formation of 1 mole of your product from. So that if I want to form this, okay, delta H of formation is the formation of that right here from its Elements. Thank you. The yawning elements. Okay. So I want to form it from their elements at their standard state. This is the special one. So delta H of formation is what I'm talking about right now. And that is formation of sodium chloride, but I actually have to write this opposite because I need sodium chloride on this side. So I'm going to write it opposite. The formation of sodium chloride from its elements, which are sodium and what's their standard state? Solid, and chlorine standard state? Diatomic gas. And I know to make one chlorine on the right side, I need half of that. That's Rohan's half. Okay, so that's the formation equation, but I've reversed it, right? Right? So if I reversed it, if I told you the heat of formation is negative 411, what is this one? 411, because I'm talking about the flipped version, so we change this. Okay, so let's make sure everything cancels that we want to cancel. Sodium solid, does it stay or cancel? Cancels here and here, like Hess's law, okay? Sodium gas cancels from here and here, good. That stays great. Electron cancels here and here. Half of a chlorine gas, diatomic, yes, that cancels there and there. Sorry, I didn't put gas, that's supposed to be gas. Okay, chlorine gas by itself cancels here and here. And then this stays. Boom. Everything's there we need. What do you do to find the last energy? Add them up. So you would do 109 plus 496 plus a half of a 243 minus 349 plus 411. And drum roll, that lattice energy is 788 positive kilojoules. Shouldn't lattice energy be endothermic?
Yes.
Yes. Therefore, we know we're in a good place there. Okay. And then we can verify that with some sodium chloride, right? Okay, let's go back and look at that chart. This chart, sodium chloride, boom, we're awesome. Just saying. Okay, right, get some like Josh said. Okay. Okay, and then this is the last thing. That's it. You guys need to know the definition of binding energy, and it's really intertwined with our group who is Clayton, actually this point, ionization energy. Energy requires you free an electron, so take an electron. And this is going to come into play big time when we get to photoelectron spectroscopy, which is an independent study you guys will have a day and a half in class to do. It's new in our curriculum, and AP has put out really good things for it, but they're all online. They're like simulations and stuff online. And then a video for me. Because I watched a webinar, because I didn't know anything about it. I had to teach myself it. We have a laptop when you're ready. And if you're doing the graph, I couldn't get any PCs. I can only send you to the media center to get PCs. Get on a desktop, and that's where you're going to have access to full Excel. Okay, so there are 4 groups. Yes. I'll do number 12 on the board. If you need help on number 12, give me about a minute. I'll let you finish
I mean, Clayton was in his field too, but he's got.
That's a block.
Yeah.
Give me a phone.
But I can also lose the 2S.
Okay, Maggie, I'm going to go over where you at. Okay. I'm going to go over number 12 from the problem set if you need it. technically, this is how this one is written. Number 12, it says a certain oxygen, certain one, some weird one, has electron configuration this. And we know that's not how you write it because we have to do times one's rule and fill up the P's one at a time and then double back. But that's how it is stated, so that's how we're writing it for now. So using that, how many unpaired electrons are there? None. Everything is paired, so there's 0 unpaired. The way that it is written, right? Second, is this an excited state? Technically, it's not considered an excited state because the electrons have not moved to an upper energy level, but it's an unstable arrangement of electrons. So I would say it's consider if you explained it as excited because it's unstable, because there's a lot of repulsion of the electrons within this small 2p sublevel, you could say excited because high energy because it's unstable, or you could say no, not excited because there is no electron in an upper energy level. As long as you explained it for me, the best answer is no, it's not excited because there's no electron in the upper energy level, but you could argue that it's unstable.
On 2px, it's 2px1, not 2.
On yours? Oh, I must have changed it on yours. So what is yours?
Does that mean that there is one?
Can you tell me, is it just
1s2, 2s2, 2px1, 2py1, 2py1, 3s1.
that's what it says on yours? My bad, I haven't updated my problem set from y'all's. Should have told me that before. So 2p x1, 2py1.
2py1, 3s1.
Oh, okay, then I changed it so there was no confusion. Let me stop. Stop now. We'll come back. Okay, so rewind. Okay. Are there unpairs? Yes, there's one unpaired, 2 unpaired electrons. Right?
Of the 2
This guy's,
and the other 3s.
those 2 are unpaired. And so, and then second question was, is this excited? Yes, this is excited for sure because you have not filled the p orbitals and you've already started putting them in 3. Right. Sorry. I haven't updated. I don't know why I haven't updated mine. And then the last question was,
About releasing energy or absorbing energy if it returns.
okay, so if it returns to ground state, it's definitely going to release energy because you're excited to release. So sorry. Ground state electron for arsenal. That looks right. Yep. L.
Just the M quantum number, what is that exactly?
Oh, that's P. So in the P's, are we talking about P's right now? One principle set up 4 quantum numbers for the single electron. So the p orbitals themselves, px, that's py actually. Z. Those are your 3 orientations, and that's what we call the ML number. It's angular momentum number. Like this, angular momentum quantum number, second one.
I just didn't know if you got it or not.
M is equal to, I'm sorry, L is equal
I wanted to get
to 1. So N is equal to, what is this one? Third energy level?
Jenny, don't think like you.
Fourth energy level?
What?
L is 1 because that's P. ML is describing which P we're in, which is a third electron over in P block.
Yeah.
So you can describe it as much as you can describe it as a +1 to represent. You can describe these as Px, Py, Pz as -1, 0, and +1. So you can say if it's a third one in, I'll go 1, 1, 1, so I'll be putting this one. And so I would call the M1 that one. But there's many options because quantum numbers, as long as you're
Then there's just yours.
as long as you're in the appropriate numbers, so this can range between -1 to +1. So really,
So that's right. So that's like number.
yeah, as long as it's 1 in each one, you're going to be a 1 in each one. It doesn't matter if you're
That's what I was thinking. I was like,
there's no other. Yeah, there's not.
What are you clicking?
Well, the default has
Dot.
dx squared, dy squared,
Our class.
dz squared, dx
How do you
squared y
say it?
squared, and dx squared minus y squared, something like that. I cannot make it.
So they're just thinking about P having.
Oh, you should, that's the other one, that's like X planar, y axis, and z. The D ones have like, it's like there's two here, so it's X and Y, and then there's like, Y and Z, and then there's like X and Z,
Yeah.
and then the donut, there's a donut one, so.
I don't know how that happened. This is like how it looks.
They look just like flowers.
Wait, when we have the microscope that can see the electrons.
We have electron microscopes that shine electrons on things and then just give us back images through light. So no, this is all. There is one. They made one that can see or detect. It's not that they can see the atoms, they can detect atoms.
And one more question. With
Yeah.
the P one, why does it start over?
Why is it what?
Like,
Started
it's like,
here.
yeah, it's like, yeah, it's like.
Because of off-balls principle. Off-ball diagram. He's the one who decided the fate. So it's because literally the energies of these orbitals follow this pattern. 1s, 2s, 2p, 3s, 3p, 4s. No 4p, you go straight to 3d. 3d is of a lower energy than 4p. You cannot go straight from 4 to 4p. You must drop an energy level. It's because of this. But instead of making you memorize this, I just show you how to use a periodic table to do the same thing. Because you always have periodic table, so why not know how to use it for everything?
I just skip a row and I start counting down and then I skip another row.
Yeah, basically. I see what you're saying.
Wait, is F the same thing where if it's like 5, you go down?
You go down by 2 though. See? You go 4D, then you go back to 5P, so you finish that row, and you go to 6S, and then that's where you get F block. You don't go to D block, you go to F block, and that's where you get 4F14. And that's 6, so that's N minus 2 when you get to F block. So N minus 2 gets from 6 to 4. And then you go to 5D, 10, and then 6S, or 6P6.
But by the way,
Alright.
there's gonna be weird stuff on mine.
There's always weird stuff. That's cool.
Found this on the ground.
Thank you.
Sure you guys is.
Yes, ma'am.
I have a thought.